So in the previous class, we did questions on normality. Do you have any doubt from the normality? Any doubt for normality?
No, sir.
Okay. Now we are moving towards the main topic of this chapter. Solubility. So see, what is solubility? In a specified amount of solvent, the maximum solute that is dissolvable or soluble, that is called solubility. So I'm gonna just define it right with me. The maximum is to it maximum amount of solute dissolved in. Please do write with me. A specified amount of solvent. A specified amount of solvent at constant temperature, because temperature do affect the solubility. So the maximum amount of solute that are soluble in a fixed amount of solvent at constant temperature, that is called your solubility. Now there is a solubility principle. So I'm going to write what is this solubility principle. Solubility principle. So solubility principle is like dissolves, like dissolves, like. That means basically in a solution, you know that two component is there, two part is there, solute and solvent. If solute is polar, then polar solute is dissolvable or soluble in polar solvent. Polar, that means charged. We will talk about this. And non-polar solute, soluble in non-polar solvent. So first of all, I'm going to take a topic that is factors on which solubility depends. Factors on which solubility depends. So there are a few factors on which solubility depends. The first one is nature of solute and solvent. Nature of solute and solvent. And this is related to your solubility principle. The second factor is your temperature. And the third factor is pressure. So we will discuss about this one by one. Just let me know when you are done with this. Then I will move to the next. Are you done with this, Austin?
Yes, sir.
So when you are going to first, we are going to talk about this pressure. So when we are going to talk about solid solute and liquid solvent. Basically, this solid solute is already compressed because it is in solid, so already compressed. So there will be no effect of pressure on this. Only the effect of gas solute, that means solute in gaseous state, in liquid will be affected. And we will talk about this after some time in Henry's law. In Henry's law. So basically, when you are going to mix this sugar in water, there will be no effect of pressure almost. Only this the solute which is in gaseous state, in liquid, that will be affected, and we will study about this in Henry's law. Okay, Umam. Just wait a minute, Rostin. Umam, are you there? So we just started our lecture with this solubility. And what is solubility? I'm going to repeat it. Maximum amount of solute which are soluble in a specified amount of solvent. So you can see maximum amount of solute dissolved in a specified amount of solvent at constant temperature, that is called solubility. And solubility has a principle which means like dissolves like. That means basically polar solute dissolving in or soluble in polar solvent. Then we are going to talk about the factors on which solubility depends. The first one is nature of solute and solvent, and this is related to your like dissolves like. And then comes your temperature. Solubility also depends upon temperature, and then comes your pressure. But when you are going to talk about pressure, you have to see the physical state of the solute. If the physical state of solute is solid, then there will be no effect of pressure. If the physical state of the solute is gas, then there will be effect, and we will study about this in Henry's law. Now, the first effect that I told you, nature of solute and solvent. Nature of solute and solvent. What is this? So it's very easy to understand. I'm going to write a point. Polar solute, soluble in polar solvent. Polar solvent. And we can write non-polar solute. Generally it happens. Non-polar solute, soluble in non-polar solvent. Non-polar solvent. So as you can see, nature of solute and solvent. Polar solute, like I'm going to take NaCl in water. NaCl in water. Water is also polar and NaCl is also polar. So NaCl will be easily soluble in water. But when you are going to talk about non-polar solute, just take an example of a CCl4, which is non-polar, soluble in benzene, C6H6. This is your benzene. And this solvent, benzene, we treated here as a solvent, and it is non-polar. So this is the solubility principle. If you have a polar solute, it will be soluble in polar solvent. And if you have a non-polar solute, then it will be soluble in non-polar solvent. So this is how solubility depends upon the nature of solute and solvent. Is that clear?
Yes, sir.
Okay. Now the next, which is very important also, comes, that is your effect of temperature. How solubility depends on temperature. Effect of temperature. I'm going to write here how solubility depends upon temperature. So before starting this, first you are going to check it whether if you are going to mix a solute in a solvent, then you have to check it whether the process is endothermic or exothermic. Whether the process is endothermic or exothermic. So if it is exothermic, then can anyone tell me, both of you, what is exothermic? Exothermic is the one which releases heat energy, heat energy. So basically a process in which heat energy is released, That means it has already a lot of energy. That's why it releases heat. And in this, if you are having a solute and a solvent, and we are going to mix it, and it is a exothermic process. That means it is releasing heat energy. It doesn't require any heat because it already has too much heat energy. And in this process, temperature, if you are going to increase the temperature, then solubility decreases. Why? Because you are not doing this. If you are increasing the temperature, it will not be in favor of this process. Are you getting my point? Exothermic, we also denoted delta H less than 0. The change in enthalpy will be negative. So basically, exothermic is the one which releases heat energy. And if you are going to increase the temperature, indirectly, you are giving heat to the system, which it doesn't require. It will be unfavorable for that system, and hence solubility decreases. Are you getting my point? And vice versa, you can do that. If you are going to decrease the temperature, solubility increases. Yes or no? Please do let me know. Are you getting my point?
Yes, sir.
Okay. And if it is exothermic, if it is endothermic, sorry, endothermic, then so endothermic, delta H here will be greater than 0. That means positive. And endothermic is a process which requires heat energy, which requires heat energy. And in this, if you are going to increase the temperature, that means indirectly you are giving heat energy to the system, to the process, which is in favor of that process, and hence the solubility will increase. Solubility will increase. Are you getting my point? Endothermic is a process which requires heat, and if you have a solute and a solvent and you are going to mix it, and if it is an endothermic reaction and you are going to increase the temperature, so it will be in favor of that process, and hence solubility increases, and vice versa. If you are going to decrease the temperature, solubility decreases. Got it? Let me know when you are doing when you are done with this. Mahmoudin Oscar, are you done with this?
Yes, sir.
Oh,
Yes, sir.
now see, there is a very important question on this, and that is you. Aquatic animals are more comfortable in cold water than warm water. Or aquatic animals are more comfortable in winter than summer. Please give me 5 minutes. I need to break the fast. And please do this question. I'm here. Can anyone give me answers? Austin, Mahmoudin.
Don't know.
So it's very easy. I'm going to explain. See what happens. Dissolution of oxygen in water is endothermic process. Are you getting my point? Now, can you answer it? If the oxygen that dissolve or that dissolve in water, that is your endothermic process. Basically, aquatic animals also requires oxygen to live, and from where when oxygen dissolves in water or in ocean or in pond, then that is your endothermic process. And if the water is hot or warm, if the water is warm, that means temperature increases, and when temperature increases, oh, wait a minute, endothermic process, I just did it wrong here. Have you written it same? Because I was telling you the correct. If it's endothermic process which requires heat energy. Okay, it was right. Sorry. I made a mistake here. So this is your exothermic. Exothermic. What I want to tell you is that when oxygen dissolves in water, it is an exothermic process. And since you have warm water, that means temperature increases. And if temperature increases for exothermic process, solubility decreases. Solubility decreases. So I'm going to write dissolution of oxygen in water is exothermic process, and in hot water or summer, due to increase in temperature, solubility of oxygen decreases. Solubility of oxygen in water decreases. So aquatic animals don't get that much amount of or enough amount of oxygen, and hence they find difficulty to live in hot water, warm water, or in summer as compared to winter. Are you getting my point?
Yes, sir.
Yes, sir.
So it's very easy. Please do right. Let me know when you are done with this.
Done, sir.
Very good. Now see, the next topic is your Henry's law, and after this class at 7:30, there will be a test from this topic, the topic that I am teaching you, like the solubility, or especially from Henry's law, because it is one of the important topic from your from this chapter. Now, what is Henry's law? So first of all, I'm gonna write the definition of it and then I will explain it. So please do write with me. Solubility. According to this law, please do write here. According to this law, solubility is directly proportional, or you can call it solubility of gas is directly proportional to pressure solubility is directly proportional to the partial pressure. I need to correct this sentence. Just wait a minute. Solubility of gas is directly proportional to the partial pressure of that gas above liquid surface. Now it's complete and meaningful. I'm going to tell you what is this. According, as I told you, about the effect of solubility in pressure, gas and liquid, we will study in Henry's. So basically, first of all, I'm going to take an example of cold drink. This is your cold drink bottle. Let's say it is your due. So, well, basically, you know that in cold drink there is liquid, and above this liquid there is gas. Whenever you are going to open the bottle, you heard a voice of course like this. So basically that is because of this gas. So according to Henry's law, the solubility of this gas in liquid is directly proportional to the partial pressure of this gas above liquid surface. That means the solubility of this gas will be directly proportional to the partial pressure that gas is applying on the liquid surface. If you are if the gas is applying more and more pressure on that liquid surface, the solubility of that gas will be more and more in that liquid. Are you getting my point? Yes or no?
Yes, sir.
So basically, solubility of gas directly proportional to partial pressure of gas, above liquid surface. Or I can write partial pressure of gas above liquid surface directly proportional to solubility of gas. So basically, this law is all about the solubility of gas in liquid, and solubility of gas is directly proportional to the partial pressure of gas above liquid surface, and I wrote it in this term. So please do write it, and we are going to derive a formula from this. Are you done with this?
Yes, sir.
Okay.
Yes.
So here we can see partial pressure. I'm going to denote it by P, which is directly proportional to Solubility of gas. Solubility can be expressed in gram per liter. That gram represent the amount of solute and liter represent the amount of solute. Or basically here in Henry's law, he took the unit of solubility as mole fraction. Mole fraction. So basically, partial pressure of gas is directly proportional to mole fraction of gas. This is your partial pressure of gas above liquid surface. The partial pressure of gas above liquid surface is directly proportional to the mole fraction of gas. And to remove this quantity proportionality sign, I'm going to use P directly proportional to, I'm going to write mole fraction of gas, and then to remove this proportionality sign, he uses its constant, that is Henry's constant. KH is the constant, and that is your Henry's constant. This is your Henry's constant. And from here you can see we got a formula that is P is equal to KH into mole fraction of gas. So please do write it. Let me know when you are done with this.
Yeah, done, sir.
Okay. Now, if I'm gonna give you to plot a graph with the help of this equation between partial pressure and mole fraction of gas in liquid and partial pressure, P stands for partial pressure. Can anyone do that? Any one of you?
So could you repeat the word?
You need to plot a graph between partial pressure and mole fraction of gas in liquid with the help of this equation. It's quite easy.
A straight line.
Yeah, straight line from where? Here, here, or
From
here.
origin to
Origin. The straight line will be from origin. Is that clear? Austin and Humamuddin?
Yes, yes.
Okay, can anyone tell me what is the slope of this equation tells you? What will be the slope? Slope, that means tan theta. We represent it by M. Slope tan theta, that means perpendicular upon base. So this is your perpendicular that represents your partial pressure. P is here for partial pressure. And base that represents your mole fraction of gas in liquid. So basically always remember that slope of this graph, that means the graph between partial pressure versus mole fraction of gas in liquid gives you can see P by X. If you have P is equal to KH, Henry's constant, into mole fraction of gas in liquid. So P by mole fraction of gas will be equal to KH. That means this graph, the slope of this graph will give you Henry's constant. It will give you Henry's constant. Are you getting my point?
yes.
Please do write. And Austin, do you know how to calculate mole fraction?
Yes, sir.
Okay. And do you know about molality?
Yes, sir.
That's good. Just wait a minute. Okay. Now I'm gonna give you a question. Molality, if you have any doubt, you can ask me. And let me give you a very easy question. Okay. First of all, the question says that am I audible?
Yes.
Yes, sir.
CO2 in water is 1.67 into 10 raised to the power 8 Pascal. At 298 Kelvin. Calculate the quantity in 1 liter of soda water. In 1 liter of soda water, when packed under 2.5 ATM, pressure at 298 Kelvin. Please do attempt. Will you be able to solve it?
Yes, I'll try.
Let me know if you are not able to solve it. See, I'm going to explain. This is the first question. First, whenever you are going to solve any numerical in physical chemistry, you need to focus what is given and then you need to write it. Henry's law constant for CO2. That means KH constant, Henry's law constant has a value that is 1.67 into 10 raised to the power 8 Pascal is given. Temperature is also given, which is not for use in this formula because you know the formula KH is equal, P is equal to KH into X. Calculate the quantity in 1 liter of soda water, volume of soda water that is given as 1 liter. And also calculate the quantity in 1 liter of soda water when packed under 2.5 atm. That means pressure is 2.5 atm at temperature this. Now you know that the formula of Henry's law that says P is equal to KH into mole fraction. Now what you need to take care is that pressure is given, partial pressure, this Henry's constant is also given, so we can easily calculate mole fraction from here. Mole fraction will be equal to P upon KH. Now I'm gonna just show you what is the pressure. Pressure is 2.5 atm. This is your atm and this is your Pascal, and to convert this into Pascal you are going to multiply it by 1.013 into 10 raised to the power 5. 1 atm is equal to basically this much Pascal. So for I'm going to write it here, 1 atm is equal to 1.0135 into 10 raised to the power 5 Pascal. So 2.5 Pascal will be equal to this much, so I'm going to write it 1.0135. 13, that is enough. So you are going to remember this conversion, it's very important. Divided by KH, which has a value 1.67 into 10 raised to the power 1.67 into 10 raised to the power what? 8. Are you getting my point? Yes or no?
Yes.
Everyone? Yes. Now this mole fraction is for gas. As I told you, mole fraction of gas, and partial pressure is also for gas. And the gas here is your basically CO2. So I'm going to apply the formula of mole fraction. I'm going to apply the formula of mole fraction here. Mole fraction of gas will be equal to number of moles of CO2. Mole fraction of CO2 will be equal to number of moles of CO2 upon number of moles of CO2 plus number of moles of water. Actually, we need to calculate the mass amount of gas or amount of CO2. So if you know the value of number of moles of CO2, you can easily calculate the mass of CO2. So concentrate here. This water, how we are going to calculate the number of moles of water? Since volume of water is given and by default, we take the density of water. Density of water, you have to remember, this is very easy. It is understood 1 gram per ml. This is the density of water, 1 gram per ml. So if you are going to calculate the mass, density will be equal to mass upon volume. And here mass will be equal to density into volume. What is your density? Density is basically, just wait a minute. Density is just wait a minute. It's density is basically 1 gram per ml. Density is basically 1 gram per ml. So I'm going to take 1 gram per ml, and volume you can see 1 liter. That means 1000 ml. 1000 ml, and ml will be cancelled, and you will be getting 1000 gram. That means the given mass of water is 1000 gram. So now you can see number of moles of CO2 and here number of moles of H2 I'm going to calculate. Given mass, that is 1000 upon molar mass, that is 18. So I'm going to put we don't know this because we need to calculate number of moles of CO2. And always remember that in Henry's law, you are going to neglect this part only because you know that in a cold drink, the amount of gas is very, very low. And that's why, and in the amount of gas is very, very low, and the amount of liquid is high, very high as compared to gas. So if you are going to add a very little in amount of very large, that will be negligible, and hence we are going to neglect it. Directly, I'm going to write 1000 divided by 18. Are you getting my point? Yes or no?
Okay.
And from here, you can see we just calculated the mole fraction of CO2 and I'm going to put it here on the left hand side. So please do write it. So here it will be number of moles of CO2 upon, we can write 1000 upon 18. So 18 will be multiplied in this numerator and 1000 will be here. And then we can write 2.5 on the right hand side. It goes, just wait a minute. I don't know why it's not working. You can write it by your own. Now it's work. 2.5 into 1.013 into 10 raised to the power 5 divided by what was the value of Henry's constant, 1.67 into 10 raised to the power. Okay. And from here you can calculate the number of moles of CO2, and after getting number of moles of CO2 you can apply given mass upon molar mass, and we need to calculate this given mass. And molar mass, you know that molar mass is 44. So you can do this. Will you be able to calculate it?
Yes, sir.
Please do it and let me know. Are you done with this?
NCO2 is 1, I got.
Number of moles you have got 1.
Number of moles 44.
Number of moles 44 you have got. After solving this, you got the number of moles 44. You
No,
can see if I'm gonna
NCO2 that
solve it.
M is molar mass, right?
This M is molar mass I already have written. I told you to calculate the value of NCO2, number of moles of CO2.
Okay, sorry.
Yeah. Okay, let's say I'm gonna explain this. If you are going to solve it, it will be like this: 2.5 into 1.013, and this 10 raised to the power 3 and this 10 raised to the power 5 combined to give you 10 raised to the power 8. And in denominator, this will be multiplied in this, and 18 into 1.67 into 10 raised to the power 8. Now you can see 10 raised to the power 8 and 10 raised to the power 8 will be cancelled. And if you are going to multiply 2.5 into 1.013, that will be approximately equal to 2.5 divided by, and if you are going to multiply it 18 into 1.67, that will be approximately equal to 30. That is basically 30.06. So you can take 30 if you want for approximation. So after getting this number of moles, just wait a minute, did I do some mistakes? No. 2.5. Now this is your number of moles, so I'm gonna write it here. Given mass upon molar mass, that is 44. So molar mass will be equal to 44 into 2.5 upon 30. So I just calculated it approximately 44 into 2.5. That will be equal to 110. And if you are going to divide it by 1000, sorry, 30, so it will be approximately 3.6 gram. So this will be the amount of. Is that clear? Are you done with this?
Yes.
Okay. Just wait a minute. Next question. This is for your homework. The next question is H2S, a toxic gas. With rotten egg like smell. Is used for the qualitative analysis if the solubility of H2S gas in water at STP is 0.195 m. Calculate Henry's law constant. Will you be able to solve it? First of all, at STP, I'm going to give you hints. At STP, the pressure will be equal to 0.987 bar. I have taken it in bar because, as you can see, you can also take it in ATM, that is equal to 1 ATM. This is also good. So please do revise whatever I taught you here, and there will be test for half an hour. Is that clear, everyone?
Yes.
Austin?
Yes, sir.
Okay. Let me know when you're done with this question. After writing, just let me know. Have you written the question?
Yes, sir.
Okay, so just wait for a few minutes. Ma'am will be joining and I'm leaving the meeting. Do you have any doubt?